Okay, this is emboss. This is fine edges. So let's look at the first one, contour, right? Contour means give me the boundaries of objects. Now it's a strange thing to ask because we are operating filters. All filters are operating at the pixels level. They look at the neighbors, top, left, north, south, east, west, maybe north, east, northwest, southeast, southwest. So the neighboring pixels, and then you start to do multiplication and addition and almost like a matrix multiplication, and you end up with the results that are being displayed like this. So what is this? This will be giving some sort of a visual clue of where the edges are. For example, this circle here could have been some sort of a hanging disc of some sort, a hanging pan, and we see that the edge of the guy that we see in dark t-shirt is not really quite visible, so we are unable to extract that boundary. But then other boundaries, like this light here, is quite visible, right? Yeah. So all these objects that are there is quite visible. And what else? All right. So there are other boundaries that if we kind of remove the whiteness, the sea of white here, we'll be able to see the boundaries very, very clearly. So these are the contours. All right. Next up is the embossed kind of outcome. Visually, sometimes we may find this very useful to kind of impress this on the wall, and this becomes quite a scene, right? I mean, it's quite interesting. And but then the purpose is not to make a sort of creative art out of it. Purpose is to create this effect. Yeah. Next up is the edge detection, a very, very well studied topic in image processing. Really, really to detect the edges. So whenever there's a change in various aspects of the neighbors, like change in intensity, change in color, depending on how you compute your edge detection filter, you can detect various edges. Horizontal, like you can tune it to be sensitive to horizontal edges, vertical edges, and that's the beginning of what is being a hot topic now about face identification, right? Face recognition, realize that there's a face there, and then recognize the face. So these are very highly intensive calculations, basing at the start on finding edges, computing these features from plain pixels. Okay, so yeah, this image, I shouldn't say that this image ends up giving very nice edge detections. Frequently, our computer vision themes will be on simple objects. So for example, this market fruit store scene will be quite complicated to a computer robot vision processor because it's unable to distinguish a lot of the edges, and so it probably will bump into the fruits and knock over a lot of baskets because the boundaries are not very well defined. So, but then if you're talking about self-driving cars looking at roads, then yeah, the cars and the roads and the tarmacs and the the labels and the traffic signs, they're quite distinct, and with proper lightings and adjustments and fine tuning, it's possible to see much sharper edges, right? Then we can start to make sense out of that using programs. Okay, good. Yeah, next up, I want to show you the actual kernel, how the image filter kernel shows itself. So let's comment out the dot shows. Okay, then we can set up a list containing the coefficients. So it's a sort of just a list, one list. It's not a nested list, right? So it's a simple Python list. I break it down in 3 lines so that we can actually see the 3 by 3 nature of this image filter. So we don't call this list a filter yet. We call this a kernel coefficients. Um, so what's a kernel? As we discussed in the classroom slides, a kernel is just a matrix. So it's either 3 by 3 or 5 by 5. Now, the current image filter supports only these two sizes, but that's pretty much sufficient for many of our intended processings. So with this 3 by 3, we give the actual coefficients. What do you want these 9 numbers to be? So imagine it's a matrix, square matrix, right? 3 by 3, that's it. So a kernel is the object that represents this internally for the filter to perform matrix operations over all 9 by 9 selections of the original source image. So once it has done that, it will come up with a result of all the matrix multiplications, right? And the outcome will be sort of deposited in a new image canvas. And this is the outcome. So image 9 is the outcome. And we scale it down to 1/6. Let's just show it first, and then we run again without the 1/6 and see what happens. Then we also created one with a top sensitive, top enhanced, top edge enhanced kernel and bottom edge diminished kernel. So we didn't leave the bottom edge to be 0. We actively diminish the intensity, yeah, and then we rescale the entire overall intensity to 1 again. So let's take a look at image 9 and 10. Original, image 9, image 10, right? As expected, image 9 is very sensitive to right edges. So right side will be enhanced, left edge will be actively suppressed, right? Diminished. Yeah. And for this top enhancement kernel, we get the top edges being actively enhanced. Unfortunately, this guy's hair is black, so really hard to enhance that. So it enhances all the top edges, and the bottom edges are actively suppressed, diminished. Okay, all right. So let's run this again. However, this time round, we let me set this to 3/6, and this is basically 6/6. Okay. So when we run this, what happens? Original, um, the left to right, and this is basically scale of 1, right? Scale of 1. So here, over here, we get a lot of sort of suppressed outcome. So the energy is not really um, shown. Yeah, okay. But over here we have 3/6, 3/6, which is giving us slightly different results. So what happens if we make it larger than 1, right? So 2, and this is 3 even. 4. Oh dear. So let's just run it. The top 2 images should be the right ones. Okay. So now we see this is a scale of 2, right? Makes it even darker. A scale of 4 makes it super, super dark. Super, super dark. Now, what is the sort of a relationship going on here? So the larger it is, the darker it becomes. So it does affect the light energy, but internally the filter divides off by this scale, right? So the larger it is, the more the darker, the more diminished the overall intensity becomes. Let's try this out. 1/6, instead of 1/6, we try 1/10. So it's even smaller than the original 1/6, right? And let's try this to be 1/20. So if you divide by scale, this is like multiplying by 10. If you divide by 1/20, it's like multiplying by 20. So what is going to happen? Well, original, 1/10, 1/20. So a lot of light, because you're dividing by 1/20. This is like multiplying by 20 the entire light energy. So at the pixel level, what happens is that when it's black, and even if the pixel is like having red 5, green 2, and blue 1, it's not totally pitch black, right? But our eyes can't tell. So it looks like black. It looks like black. But there are some noise on the ground, right? So it's 5, 3, 2, even 20, even we can't see. It's still black. But when we multiply that by 20 times, all these tiny noises will be magnified to some sort of a visible color. And the already brightened edge, it's already full 255. When you multiply it some more, it's being clamped. So it's being maxed out at 255. It stays at 255. So there's not going to be sort of a explosion error or whatnot, but it'll be clamped at 255, making those pixels that are already white still white. But the net effect is the pixels that are having noisy black, noisy black as in they are not fully 000. They are having ones and twos and tens and fives and 20s. They become visible. So this is exactly the kind of effects that we want if we want artistic effects, right? So if we want some sort of like uh, luminescent kind of Twilight Zone feel to this night market, maybe this is nice. This is great. But if you are looking for this top edge computation to detect perhaps rising sea level, so the waves are coming, you have a camera looking, you want the top of the sea level to kind of do an automatic calibration or measurement of how high the tide is, then this is a lot of noise and it's not very helpful for us to detect where the top of the wave is. Yeah, so it all depends on what applications you are in. There's no standard answer to what is the right scale to do. Okay, next up we are going to look at drawing and texting, composing new images. So let's do that. Okay, so let's begin by first of all suppressing the shows so that we don't get a lot of pictures popping up. Then, just going over to the slide, let me copy and paste the drawings. So first thing first, you must import the image draw submodule, right? Because we need a drawable. So remember, image itself cannot be drawn, but we must make a drawable version of the image. So by creating an image draw, so it's a bit like the image filter, right? Create a filter. So image draw. The source is and destination is image one. Create a drawable over image one. So whatever we do to drawable, like in this case, draw a line. Drawable, draw a line, dot line. Starting from 50-50, draw until 150, 250, with a color that is reddish in color and a width, a thick line, 20, right? So when you do that, then the drawable will draw a line onto the image img1. So this model is how Pillow implements the drawing mechanism. I say this model because it could have been done in many other ways. Different Windows systems will implement it differently. It may not be drawable. It may be just img1.line. Some modules may choose to do that, but remember this is how it works in Pillow. So if you want to make use of Pillow, just follow this convention and things are done nicely. Okay, so we ask for the width and height of image one, and then draw an ellipse, and we talked about this. Calculate the top left, so minus 200, minus 200, and the bottom right, so center, offset by 200, offset by 200. So top left to bottom right, this within this box, draw an ellipse. If you give a rectangular box, it will really draw an ellipse because it's kind of a sort of distorted circle. But here we give a square, so the ellipse will look like a circle. Color is green. Don't fill it. So if we fill it, it will become a solid disk, overwriting the original image, and have a width of 15, and then draw a rectangle. Yeah, so we need to then show it. So image one dot show.